Alright, next video, molar enthalpies. So molar enthalpy is represented as a delta Hx, and this is the definition. It represents the enthalpy change associated with a physical or nuclear or chemical change involving 1 mole of substance. Really crucial there. It's per mole of substance. The X will stand for the type of change occurring. So there's different delta Hx's. For example, you can have delta HSOL, which means the molar enthalpy change for a solution, dissolving a solid. You can have KCl, solid going to K plus and Cl minus, AQ, or it goes to KClAQ. You can write it as the ions here, or you can write it as the compound, but both have to have AQ. Either way is acceptable. You're going to have delta HCOMB, which is the molar enthalpy of combustion. So here's an example of combustion of propane. If you barbecue, that's the chemical reaction that occurs. Delta HVAP, or vaporization, where you're going from a liquid to a vapor, a gas state. You can also have molar enthalpy of which is neutralization, and you would have to state whether it was for the acid or the base that was actually consumed. For example, here we've got sodium hydroxide and sulfuric acid. So when you represent your molar enthalpy of neutralization, you would have delta H neutralization for NaOH, or, delta H neutralization for H2SO4. So the enthalpy change that we've been introduced to already, delta H or delta HR, so the enthalpy change for the reaction, we've been introduced to. The units for this are in kilojoules. But molar enthalpy, its units are kilojoules per mole. You've got to remember that these two are very different quantities. So we can relate these two terms using the following relationship. So the enthalpy change for the reaction, or delta HR, is equal to the number of moles times the molar enthalpy. So the enthalpy change for the reaction actually depends on how much substance was used. So the total energy for the reaction total energy change for the reaction depends on how much matter is changed. And it doesn't matter if it's physical, chemical, or nuclear. The reaction, for the reaction, the formula is the same. Okay, so let's do a couple of examples. The molar enthalpy of vaporization. So delta H vape for water is 40.7 kilojoules per mole. So this is an endothermic process because that is a positive value. If 180 grams of water are vaporized, how much energy is involved in the change? So we have mass of water We have the molar enthalpy of vaporization. We also know the molar mass of water, which is important to find moles. So, we want to know how much energy is involved in the change for 180 grams. Well, if 1 mole represents 18 grams of water, we know we've got a lot more moles of water, so we're going to have a lot more energy absorbed. Okay, so let's plug in our numbers. You can do it in one step or more than one step. Because moles is equal to mass divided by molar mass, you could either solve that first or plug it in here. Mass divided by molar mass times the molar enthalpy. And this will give you your enthalpy change. Or you can calculate your moles separately and then plug those into your equation. If you plug them in, make sure you carry extra significant digits so you don't introduce rounding errors. This is equal to 9.9889 moles. So we would plug that in now to delta H is N delta H vape. And that is 9.9889 moles times 40.7 kilojoules per mole. Let me get this out of the way. Okay. So multiply those two numbers and you get 406, sorry, that's a 4.548 kilojoules because your moles cancel. So we have 3 significant digits here, we have 2 significant digits here, so our final answer should be rounded to 2 significant digits, so 410 kilojoules of energy are absorbed. For those of you that still like dimensional analysis, you could do this without formulas. We have to find how much energy is involved in the change. So we know we have to find kilojoules. So kilojoules in our final answer, the only ratio we have with kilojoules is our molar enthalpy, kilojoules per mole. We have this ratio, 1 mole for 18.02 grams. Moles have canceled, and then we have 180 grams. Grams cancel. The units we have left are kilojoules, so 40.7 times 180 divided by 18.02 is 410 kilojoules of energy. Okay, let's do the next problem. Okay, so the molar enthalpy of fusion or melting for water is 6.01 kilojoules per mole. So that's delta H melt. And what is the energy change when 1 kilogram of water is frozen? So we've got a mass in kilograms, but we're going to end up needing it in grams, because we have to convert from grams to moles. So 1 kilogram, always show your work if you want full marks. So 1.00 times 10 to the 3 grams. It's the easiest way to show it. The molar mass of water is still 18.02 grams per mole. We're asked for the energy change when 1 kilograms of water is frozen. Freezing is the opposite of melting, so you have to change your molar enthalpy to the molar enthalpy of freezing. The quantity is the same, but because it's the opposite process, it's the opposite sign. So when water freezes, it's exothermic. When it melts, it's positive, it's endothermic. That's all the sign means. One is energy is released, one is energy is absorbed. So you can either calculate the number of moles or plug that into this equation. So we've got 1,000 grams. We know the molar mass, so this quantity will give us the number of moles. And then our molar enthalpy of freezing is negative 6.01 kilojoules per mole. So when you do your math, you get 333.518 kilojoules, and it's negative, so it's exothermic. And we have 3 significant digits in our initial data, so our answer is 334 kilojoules of energy is released. Again, if you like dimensional analysis, because we're asking for energy change, we need kilojoules in our first ratio on top. We need to get rid of moles because it's on the bottom. 1 mole contains 18.02 grams of water, and then times 1,000 grams. And the answer is the same, 334 kilojoules. So this process releases 334 kilojoules to the environment. We can use calorimeters to find molar enthalpies, so this is an experimental technique. During this unit, we're going to use the calorimeter quite a bit, and you're going to need to understand some important details. Calorimeter is a device to use to measure the change in energy of a system. So it allows us to measure the change in temperature. So you can have simple calorimeters like a coffee cup calorimeter, or it can be more complex like a bomb calorimeter. You can look up pictures of those. The calorimeter is the surroundings for the experiment. So Q equals mc delta T, that part of the formula refers to whatever we are measuring the temperature change of, so in the calorimeter. The enthalpy change refers to the system, so delta H equals N delta HX is for what the change is that you're measuring inside the calorimeter. Don't get these masses confused. There are assumptions that we use in calorimetry. No heat is transferred to the outside environment from the calorimeter. We assume that it's an isolated system. Any heat that's absorbed or released by the calorimeter materials are negligible. Obviously, a bomb calorimeter is a little more efficient at this than a styrofoam cup, a simple calorimeter. And a dilute aqueous solution is assumed to have density and specific heat capacity equal to pure water. So the density is 1 gram per milliliter. The specific heat capacity of the solution is 4.19 joule per gram degrees Celsius. Or if you're dealing in kilograms, you've got large quantities, you can do kilojoules per kilogram degrees Celsius. You will encounter two kinds of calorimetry questions. So water is used in many of the experiments so that you can easily measure the temperature change. So in that case, you take the mass of the water to be the mass for the calorimeter. So you have two solutions mixed together in a reaction. Like it could be a double displacement reaction. You have to add the initial volumes of the solutions together to get a total volume and convert that to mass. And that's the mass that you use in the calorimeter mathematical equation. To find the moles for the enthalpy equation for the system, you need to look at the molar concentration of the solutions in question. So you will need to use C equals N over V, or concentration times volume is equal to the moles. So let's do a couple of questions. We have 9.96 grams of lithium chloride dissolved in 100 grams of water that's sitting at 22.2 degrees Celsius. Temperature of the water rose to 41.3 degrees Celsius. What is the molar enthalpy of solution for lithium chloride? All right, what do we have? We have a mass of lithium chloride. Lithium chloride is being dissolved, so that has to do with the system. We have 100 grams of water, and we know the temperature change of the water, so this is the mass involved in the surroundings. It started at 22 degrees Celsius. It finished at 41.3 degrees Celsius, and we are looking for the molar enthalpy of solution for lithium chloride. We are looking for delta H solution for lithium chloride. All right, so let's start with our cue, our surroundings. So our surroundings is the water. The mass is 100 grams. The specific heat capacity of water is 4.19 joule gram degrees Celsius. And we need our delta T. Delta T is always T final minus T initial. So 41.3 minus 22.2 degrees Celsius, which is 19.1 degrees Celsius. Okay, stick the numbers in your calculator. 8,002.9 joules. So the surrounding water for this reaction increased in temperature, so the energy that it absorbed was 8,002.9 joules. That energy came from the physical change of dissolving the lithium chloride from the system. So the system and the surroundings are equal in magnitude but opposite in sign. So now we know the enthalpy change for 9.96 grams of lithium chloride was 8,002.9 joules. That is only for this specific mass of lithium chloride used. So now we plug that into the second equation. Now we're dealing with our system. We want to solve for the molar enthalpy, so we move the number of moles to the other side. Delta H divided by N. So we have 8,002.9 joules divided by the number of moles. The number of moles is 9.96 grams divided by the molar mass of lithium chloride, which is 42.39 grams per mole. So you can either calculate that and substitute it in, or plug that into this equation. So 9.96, which is 0.23496 moles. Okay. So this is equal to 34,060.535 joules, it's negative, per mole. Change joules to kilojoules. There's 1,000 joules per kilojoule. So you divide that by 1,000, and 34.06 or 34.1 kilojoules per mole is our molar enthalpy of solution for lithium chloride. So for every mole of lithium chloride that is dissolved, 34.1 kilojoules of energy will be released. So the beaker will get hot. Here's an example for if you're mixing two solutions together. So this is a chemical reaction. We've got 50 milliliters of copper 2 sulfate mixed with an equal volume of 0.6 molar sodium hydroxide. They produce a precipitate of copper 2 hydroxide and a solution of sodium sulfate. The initial temperatures of both solutions 21.4. After mixing, the highest temperature is 24.6. Determine the molar enthalpy change for copper sulfate. So in this question, you'll notice they specifically told you which compound they want you to use in terms of your molar enthalpy. So that is going to be our system. So our moles for our system are going to come from copper 2 sulfate. All right, so let's collect the information that we know. We have a solution of copper 2 sulfate, and we have 50 milliliters. We have 50 milliliters of sodium hydroxide. So our total volume is 100 milliliters. We have to convert that to mass using the density of water, because we're assuming that these are so dilute that that is actually the same density. So we have 100 grams of solution in our beaker. So this is going to be the mass for our surroundings. We put the thermometer into the beaker, into the reaction, so we need to know the mass, total mass of the solutions when they're mixed together. All right, so we can set up our Q. You always start with your Q when you're finding molar enthalpy. So 100 grams times, again, we're assuming it's water, so we use the specific heat capacity of water. And our temperature change is 24.6 minus 21.4. You could just calculate that before you plug it in, or you can show your calculation there, like that, but basically it's 3.2 degrees Celsius. So, plug these numbers in your calculator, and you get 1040.8 joules of energy. You can, if you want, convert this to kilojoules here, or you can calculate it to kilojoules after. It doesn't really matter. You must write the statement so we know that the enthalpy change for this quantity of these concentrations will involve the energy change of 1040.8 joules. So far we've got Q, and now we've calculated delta H, so the energy change for the system in this situation. So now we need to find the moles of our system. So we're going to use moles is equal to the concentration times the volume, 0.3 moles per liter times, your volume has to be in liters, so we have 0.015 moles of copper to sulfate. So now we're going to plug that into our equation. The enthalpy change is equal to the number of moles times the molar enthalpy. So now delta Hx is delta H, enthalpy change, divided by the number of moles. So 1340.8 joules divided by 0.015 moles is equal to, so this is 89,386.66 continued joules per mole. Divide that by 1,000 to get your kilojoules. Negative 89.4 kilojoules per mole. So for this reaction, the enthalpy change, the molar enthalpy for this reaction with respect to copper to sulfate is 89.4 kilojoules per mole. So molar enthalpy is the energy change that is involved with the changing or chemical reaction. So, molar enthalpy, delta Hx, is the change in enthalpy for a physical, chemical, or nuclear change involving 1 mole of substance. So if you're given data, no explanation, if you're given data and you see the units, kilojoules per mole, that is the molar enthalpy. To figure out how much energy is released, you have to multiply it by the number of moles to figure out the quantity of energy released for the specific quantity involved in the reaction.